Hello and welcome back to Physics Online, in which we're going to continue our graphical analysis. And look at this wild looking graph. It's a velocity in meters per second versus time graph. And what I would like you to do is it basically describes the motion of, we'll say, a toy car. What I want you to do is describe this motion for each time interval. In other words, express it in words. What's happening between 0 and 4 seconds? What's happening between 4 and 7 seconds? Between 7 and 13 seconds? In fact, what's happening right at that point at t equals 13 seconds? So push that pause button and write out some answers to these. All right, let's see what we have for answers. First of all, between 0 and 4 seconds, well, the velocity is increasing, right? It goes from 0 meters per second all the way up to 4 meters per second. Then from 4 to 7 seconds, from 4 to 7, well, this cart is moving at a constant velocity of 4 meters per second. Then it starts to slow down. So between 7 and 13 seconds, right? Then we have a decreasing velocity. In fact, we go from 4 meters per second all the way down to 0 meters per second. In fact, that is the answer to our last question. What happened to the cart at t equals 13 seconds? Well, it came to rest. How about if this graph were to continue? If it were to continue and look something like this. Now, what do you think the description would be? Well, keep in mind, here's my axis, my velocity axis, and if we continue downwards like this, okay, then we're talking about negative values. So basically, the velocity would be negative. Remember, velocity is a vector, so what we're saying is that when it becomes negative, it's going in the opposite direction. So in review, we have an object starting at zero velocity, moves away from its starting point, then it moves back toward its starting point, decreasing its velocity, and then it actually stops, and then it goes in the opposite direction. It has negative velocity. All right? Let's go on and take a look at another aspect of this graph. Let us find the area between the graph and the time axis for the first 4 seconds. For the first 4 seconds, what are we talking about here? We're talking about this region right in here. In fact, let's see if I can. Talking about this region right here. We want to find this area right in here, right? And basically, that is a right triangle. And hence, the equation would be 1/2 base times height. So when you're asked to find the area, make sure you put down the equation with no numbers. The base now, look at the base, 0 to 4. This is in seconds now. So put in the units, 4 seconds. The height right here of our right triangle is 4. It's 4 meters per second. Put in those units. And as you should be able to see here, the seconds cancel. That cancels, and that cancels, and we're left with 8 meters. Okay? So in other words, what we have found is that this toy car has traveled 8 meters in that first 4 seconds. And we could also express our answer as delta x, that's the change in position, is equal to 8 meters. All right? Let's go on. We see that this area gives us the displacement of our car during the first 4 seconds of motion. What I want you to do is calculate the car's displacement during the time interval between 4 and 7 seconds, that is between here and here. All right? What is the displacement during that particular time interval? And you can make basically a little rectangle talking about this region right in here between 4 and 7 seconds and come up with the equation for a rectangle. And then finally, we're asked to find the car's displacement during the time interval between 7 and 10 seconds. 7 and 10 seconds. Let's see, between 7 and 10 seconds, that's here and here. Now this one's a little tricky. We're talking about this region here and here, like this. Okay, and what we want to do is divide this up into a triangle in which we can find the area of that triangle using 1/2 base times height, and a rectangle. We can find the area of this rectangle. See, using the base times the height. And then when you sum those two quantities up, you will have found the displacement that this car attained between 7 and 10 seconds. Okay, and then what else do we want to do here? Then we want to calculate the total displacement of the car during the first 10 seconds of motion. That is, we're talking about from here, from 0 all the way up to 10 seconds. So you will end up adding up this area and this area and this area and this area. So push that pause button and let's see what you come up with. Use your supplement, get out that calculator, and we'll come back and compare answers. Okay, let's compare answers. First of all, the displacement during the time interval between 4 and 7 seconds. It was indeed a rectangle. We take a look at our graph up here, and our rectangle is this region right in here. And we can see the base is 1, 2, 3 seconds. The height is 4. 3 times 4 is 12. So it gives us 12 meters as the displacement that took place when it was traveling from here to here. What about the displacement between 7 and 10 seconds? Well, we broke it up into a triangle. The area for a right triangle is 1/2 the base times the height. The base is, as you can see, is 1, 2, 3 seconds. The height is 2 meters per second. Seconds cancel, and I get 3 times 2 is 6. 1/2 is 6, 3 meters. And then the rest of this is a rectangle, base times height. The base is 3 seconds, and the height is 2 meters per second. Notice that the seconds cancel, and I get 6 meters. So we sum these two up. 3 meters plus 6 meters gives me 9 meters. So 9 meters of displacement was covered when it went from this particular velocity to this particular velocity, that is in that short time period. And we go down here and we can check those numbers. There it is, 9 meters. Now to get the total displacement of the car during the first 10 seconds of motion, you simply sum up what we found thus far. The first 4 seconds, it was 8 meters. Then the next period of time, the displacement was 12 meters. And then the last portion, it was 9 meters. Add them all up. And let's see if I did my math right. Yeah, it looks like 29 meters. And by the way, if we take a look at our graph and ask ourselves, what would be the situation if we take a look at, let's get my thing here. Suppose we wanted to know this displacement right in through here. We'll say this was 15 seconds. Well, we would have to find the area of this little right triangle. In other words, whenever we talk about the area on the graph, we're talking about between the graph and the time axis. And this is the same situation. Here's the actual graph. If it went in the reverse direction, here's my time axis. We would have to find the area of this region right in here using my equation for a right triangle. And keeping in mind that one of the velocities was negative. Okay, one of the factors was negative, and therefore the displacement would be negative because, as we said earlier, it's going backwards. So what we've learned here is that, first of all, whenever we have a velocity versus time graph, we can find the displacement by finding the area between the graph and the time axis, whether the graph is up here or if the graph extends in a negative direction. It's always between the graph and the time axis.